Okay, so we've been talking about really a type of reaction which falls under the big category of double displacement reactions. And that is always really the reaction that you get when you have two ionic compounds coming together, which basically means you have basically two cations, two anions, so a positive negative guy and another positive negative guy. Again, the cations will always switch partners in these type of reactions. And really, in terms of a more specific type of double displacement reaction we've been talking about here, we've been talking about precipitation reactions, which are at the core a double displacement reaction, but they are also sometimes classified as precipitation reactions because they actually will form a solid or a precipitate as a result of those ions basically switching partners. We were finishing up on talking about how we could kind of determine whether or not when we put together a couple of ions, will we expect a solid to form or not a solid to form? And again, we use our solubility rules here to do that. So I think that's where we left off. So using the solubility rules for each of these, determine whether or not that they Okay, so let's take a look at this. We'll start with the first one. I see potassium, which is a member of group 1. That's pretty much as far as I need to look. You can also look at the hydroxide if you want, but really that's as far as I need to look. That's soluble pretty much in everything. So we would expect this to be soluble, and it would get the aqueous or symbol next to it. Looking at silver bromide here, we would want to look at our solubility rules for bromide, which is soluble in everything. But there are 3 exceptions. Silver, lead, and mercury are the exceptions. And in this case, we did hit one of the exceptions, which obviously is silver. And that would mean that instead of being soluble like it normally would be, it would be insoluble in this case and would have a solid for it because it is the silver attached to the bromide. Any questions on that there? Looking here at calcium chloride, once again, we can look at chloride, which is a soluble in everything except for, bless you, what we just talked about a second ago. Those 3 guys, silver, lead, or mercury. And in this case, there is no silver, lead, or mercury. So we would expect this to be soluble, and it should be the aqueous symbol. Looking at the next one, which is lead and nitrate, it is really the nitrate here that we'd probably want to focus in on. And nitrate is soluble in everything. There's no exceptions, which means pretty much that's as far as you need to look. So you know that that is going to be aqueous and no solid. Lastly, here we have lead to sulfate. Again, you would want to look at the sulfate, which we do see here. And again, the sulfate is aqueous normally and soluble. But as we can see on the right-hand side, lead is one of the exceptions. So instead of being soluble, it will be the opposite of that, and it will be insoluble in this particular case based on solubility rules. It should have a solid next to it now. Any questions on, again, how to use solubility rules? You should be familiar with the solubility rules. They may be provided for you most likely, but you should have some familiarity with it. Yeah. So once again, they will be provided for you, but you should have some familiarity with it. Yeah. Yep. Other questions? All right. So when we're talking about writing net ionic equations and our total ionic equations, again, we want to break apart anything that's a strong electrolyte into ions. Once again, anything that's a weak electrolyte, a solid, liquid, or gas will stay together. So we actually did this equation a second ago when we were looking at solubility, so we'll just write it up here. All right, so why don't you write the total ionic equation for this guy? Why don't you write the net ionic equation? And why don't you also figure out the spectator ions? So why don't you take a moment and do that? Again, I think we did this guy with solubility rules a minute ago. Right up there. Okay, so let's take a look at this. Once again, just predicting the other side, and you should be able to recognize it's a double displacement reaction, as you do have two ionic compounds. Again, a positive guy and a negative guy, a positive, negative, and they will switch partners, which again is how we know what we ended up with. And that's how we did get, again, our products over here. The silver will hook up with the negative chloride. And again, our other guy there, our positive sodium will hook up with the negative nitrate and form our opposite sides. So that is, again, how we got our products. It is balanced. We do want to break it apart into our total ionic equation. I'll just call it TIE. The silver nitrate is a strong electrolyte, which means it will break apart into a silver ion plus a nitrate ion. The sodium chloride will also break apart into sodium ion and a chloride ion. We do have our solid that is formed. So as we talked about, we do keep it together. Otherwise, it would not be a solid. And our sodium nitrate is a strong electrolyte, which will break apart into a sodium ion and a nitrate ion in this particular case. And that would give us our total ionic equation. Any questions on that one there? Now, again, it is always really kind of the total ionic equation where we can look on both sides of the arrow and we should see, again, ions that look exactly the same. And in this case, we have nitrate, and we have sodium and sodium in this case. And these guys, again, are going to be our spectator ions. And as we talked about, they're essentially just kind of hanging out and watching what's going on. And in this equation, we do cancel them out. You can think of the arrow like an equal sign. It just kind of subtracts off from both sides. And that's going to leave us our net ionic equation, which is what is really taking place in this reaction, which is the silver ion plus the chloride ion are going to come together and make silver chloride our solid. And again, our precipitate in this case, and really the driving force for why this reaction will take place is those two guys coming together. Again, as I mentioned a number of times earlier, you want to make sure that when you are writing these equations, especially the total ionic equation and the net ionic equation, that any one that is an ion has charges in the actual formulas. Yeah. Okay, so let's take a look, see how you're doing. So we have everything in Word. So as we've been talking about, we want to make sure we get the right formulas first. So potassium carbonate, potassium is K plus, carbonate is CO3, 2 minus. So when we put that together, we do need an extra K. So that's a K2CO3. We have nickel 2 chloride. That is a nickel with a +2 charge. Chloride is a -1 charge. So once again, when we put that together, just like we did with naming, we should end up with that. So that's really our starting process here, K2CO3 plus NiCl2. This is also obviously two ionic compounds, which are going to switch partners. So they're going to do a double displacement reaction, once again, by switching these partners. So again, we want to put it together properly. So we're going to go on the other side and take potassium, which is just K plus, and we're going to put it together with chloride, which is Cl minus, and that gives us only KCl. Again, does not give us K2Cl2. We will then put our nickel, which has a +2 charge, together with our carbonate that has a -2 charge, and that gives us our proper form of NiCO3. First off, any questions on putting it together there? Once we have it together in the sense of our proper formulas, like we've talked about before, it's at this point that we then need to go back and make sure it's balanced, which again, in this case, it is actually not balanced. So to balance this guy up. It looks like perhaps we need a 2 right about there in terms of our potassium and our chloride, and that gives us 1 nickel, 1 carbonate each. Now that we have the formula and it's balanced, we can use our solubility rules to decide, what's going to be our precipitate here. We see potassium in our first one, which is all we need to see. And we know that's always going to be aqueous because it's soluble in everything. We see the chloride in the second one, and we know chloride is soluble in everything except for silver, lead, or mercury, which is not the case in this one since we have nickel. So we know that's going to be soluble. Potassium here tells us it's going to be soluble by process of elimination, or if you look at your solubility rules, it is going to be our nickel to carbonate here that's going to be the solid. Any questions on that? And again, you can refer back to obviously our solubility rules there. Carbonate going to be insoluble except then when it's hooked up with something in group 1, and obviously it's with nickel, which is not part of group 1, which means it should still be insoluble. All right, that would then give us our molecular equation. We now can write our total ionic equation by breaking this guy apart. And our 2 for our potassium will come in front, and that means that we have 2 potassium ions plus a carbonate, as this guy will come to the front. With our nickel, it will also break apart. That's a nickel with a +2 charge. And this 2 will also come in front of the chloride because it means it has 2 Cl minuses. It does not mean that you have Cl2 minus, which is not existing. On the product side, the 2 will get distributed to both guys behind it. That means we have 2 potassiums and 2 chlorides. And as we've talked about here, our solid will remain together. Otherwise, it would not be a solid. And that would give us our total ionic equation, which is properly balanced as well by distributing those coefficients and those subscripts properly in the total ionic equation. Any questions on that one there? Looking on both sides here, we're going to find our spectator ions, and it looks like in this case, potassium and chloride looks like our spectator ions. So those 2 should be our spectator ions in this case. Right, like that, ions. We will cancel them out from both sides of the arrow, and that's going to leave us our final equation, which is our net ionic equation. And basically what's going to happen in this case is the nickel ion is going to find the carbonate, and it will form this precipitate of nickel to carbonate. And that again is the solid that is formed. Any questions on any of those there? Again, I would say most people struggle a lot with you have an empty arrow on the right-hand side and getting the correct formulas down and balancing them correctly. And also forgetting to write charges on ions as you go through these different equations. Any questions on that one there? Let's try a couple more here just to make sure. Just the one we just did. All right, so for these, see what you come up with. Finish the equations and write the total ionic, net ionic, figure out spectator ions, see what you get. And we got to predict what's on the other side of the arrow. So as we've been talking about, we want to make sure we first get the proper formulas and then worry about the balancing. Again, that's the proper order. We also should be able to, at this point, recognize that this is a double displacement reaction as we have 2 ionic compounds coming together. And we know always in that situation that we're going to get this switch of partners that's going to happen. Once again, when we predict what goes on the other side, we want to just take the basic units of each of these things. So KCl is K plus and Cl minus. Silver nitrate is silver with a +1 charge and nitrate with a -1 charge. Now we could put together our opposite guys correctly. So the K plus and the NO3 minus will come together again to give me KNO3, as I just need 1 of each. Here, the silver, which is +1, and the chloride, which is -1, also will just need one of each and they will come together. Now I do have my proper equations down or formulas. Now I can look at balancing, and in this particular case, we're actually balanced here. Everybody's good. There's one of everything basically up there, one potassium, one nitrate, one chloride, and one silver. Now we can use our solubility rules to help us. They did the guys on the left. Once again, when we see potassium, that's really as far as we need to look. It is soluble in everything. In addition, nitrate's also soluble in everything, so you don't really have to look any further than that one either. Here we have silver chloride. Again, we would look at the solubility rules for chloride, and that is soluble in everything except for silver, lead, and mercury. And in this case, obviously, silver is involved, which means it would be the opposite, and that would be our precipitate that would come as a result of that. Any questions on that there? Now, this is obviously our molecular equation. We could write our total ionic equation. Remember, anything that's a strong electrolyte will break apart. Everything else will kind of stay together. So that's going to give us a K plus and a Cl minus. The silver nitrate will also break apart into a silver ion and a nitrate ion. Potassium nitrate on the right-hand side, also a strong electrolyte, breaking apart into a K plus and a nitrate. And once again, as we've talked about, our solid, because it's a solid, will have to stay together in this case. And this will give us our total ionic equation. Now that we have our total ionic equation, it is looking for our spectator ions. So again, we're just simply looking for what is the same ions, exactly the same. And as I mentioned earlier, should also be the same amount on both sides if you properly balance the equation. So potassium is the same, and chloride here is going to not be the same. So it's actually going to be nitrate, would be a better one to grab there. Nitrates on both sides. There he is right there. Nitrate and nitrate. Perfect. And again, these are going to be our spectator ions that we cancel out. That's going to leave us our net ionic equation in this case of what's really happening when we mix these two solutions together is the silver ion and the chloride ion are going to come together to make this precipitate of silver chloride. So once again, when we kind of throw this into the beaker, we have potassium ions, we have chloride ions, we have silver ions, and we have nitrate ions. And when we actually do toss it in here, it is these two guys coming together to make a white solid, and we will have our potassium ions and our nitrate ions still floating around basically in the solution part of it. So they're still there. They're just obviously not forming the solid that is being made. Any questions on any of those there? Looking at the second equation, we're going to take the same approach. And again, we should also recognize in this one, it is an ionic compound. So plus minus, plus minus. So we're going to get that double displacement. So in this case, we have a sodium ion as the basic unit and a sulfide. This is a calcium with a +2 and a chloride with a -1. Once again, not Cl2 minus, so just Cl minus is the proper ion in this case. We're going to switch partners, so these guys are going to come together. And again, when we put it together, that's a +1 and a -1, which should give us NaCl. And our +2 for our calcium and our -2 will actually give us CaS in this case. Again, no Na2Cl2. So again, you want to put it together correctly. At this point, we could actually balance it, and we do need a 2 there, I think, in front of the sodium. And I think that will balance it up. Any questions on how we got there? Using our solubility rules, sodium chloride. Sodium is as far as we need to look. So that is going to be aqueous. If we look at sulfide here, and we back it up to take a look just so we can see it there. Our sulfide is right here, and it is typically insoluble. But one of the exceptions, though, happens to be calcium in this case, which is what it is hooked up with, which means it's actually going to be soluble in this case. So that combination, based on our solubility rules, going to be soluble, which means that we will get an aqueous in this case. Yeah. First off, any questions on that? So if we look at our molecular equation, we write our total ionic equation. In this case, we will get 2 sodium ions that will break apart because it's a strong electrolyte. We will get a calcium ion that will break apart. We will also get 2 chlorides as we move the 2 in front. The 2 in front of the sodium chloride will get distributed. So we'll get 2 sodium ions and 2 chloride ions. And our calcium here, let's go underneath, calcium ion and a sulfide ion in this case, yeah? So if we look at our spectator ions in this case, I have 2 sodiums on the left and right, so they cancel. I have 2 sulfides, or actually a sulfide on the left and the right, they cancel. Calcium on the left and right cancel. Chloride, 2 of those cancel. I'm left with nothing in this case, yeah? So did a reaction take place? No reaction took place, yeah? Remember, for a reaction to take place, you pretty much need a solid, water, or electrons being transferred, and none of those things actually took place in here. You basically just got a beaker of ions floating around, nobody coming together in this case, and we actually would get no reaction in this case, as they would all, obviously see, cancel each other out. Yeah. Any questions on that there? Yeah. Technically, they're all spectator ions. Technically, there's really no reaction happening in this particular case. Typically, usually the spectator ions are usually when you have some type of reaction happening, they're the ones still floating around. But technically speaking, all these are still floating around. So they all would, I guess, be spectator ions, which would lead you to really no product being formed, no solid, no water, no electrons being transferred in this type of reaction. So it would lead to really no reaction. Everybody's just kind of floating around free in the solution. Question. Okay, so let's take a look here. So once again, we're giving our kind of starting guys, our NH4 SO4, so a little ammonium sulfate with some lead 2 acetate. And again, the recognition of that's an ionic compound, positive, negative guy. Positive, negative, again, should tell you it's a double displacement reaction. We're going to switch partners. Again, we want to look at just the basic units here. So that is the polyatomic ion of ammonium, and that is sulfate, also a polyatomic ion. For lead 2, knowing that it is lead 2 is helpful. And this is acetate, which is, again, the basic unit here. So now we have our basic sort of units as we switch partners. And again, on this side of the arrow, we want to put it together properly. So that's going to be +1 and -1 coming together, which is going to give us NH4 C2H3O2. And here, that's going to be +2 and -2 coming together. And that's going to give us a PbSO4. Again, I'm not worried about the balancing here or anything like that. I just want to get the right formulas down. Now I can worry about the balancing. I got my 2 ammoniums on the left and 1 on the right. So I'm going to put a 2 there. That gives me 2 acetates, which is what I need on the left as well. And I got 1 lead and 1 sulfate. So now I do have a balance. Again, any questions on that? Really, where a lot of people super struggle with is like trying to get the right formulas on the right hand side or predict the correct formulas, because a lot of times, like I said before, people try to do the balancing and the equations at the same time. Any questions on that? Looking at our solubility rules here, clearly we know it's aqueous because it tells us, but we would know it as well because of the ammonium. It's soluble in everything. And here our acetate is also soluble in everything. So we know that those 2 guys are going to be aqueous. By the way, the key was they also told you that those guys are aqueous right there. On the other side, we see the ammonium with the acetate, which clearly means it's going to be aqueous. And lastly, here we have sulfate, which will be insoluble when it hooks up with lead. So that should be our solid in this case. Any questions on that there? You didn't have to do it here, but if you did break it apart into its total ionic equation, we would get 2 ammoniums plus a sulfate. Our lead would break apart into lead 2, and that 2 for the acetate would come in front, and we would have 2 acetate ions. That 2 here would go to both of these guys when we break it apart, so we'll have 2 of the ammoniums and 2 of the acetates. And again, I'll go underneath since I ran out of the room there, and we would have our lead 2 sulfate staying together as it's a solid. Our spectator ions in this case would be the 2 ammoniums and also the not the sulfates, keep circling the wrong one. The acetates there would be our spectator ion in this case. Those guys are going to cancel out and again leave us with really the net ionic equation, which is when we pour these guys together, it is the lead ion is going to go find the sulfate, and they will come together to make this solid of lead 2 sulfate, which again is a precipitate that was made, a precipitation reaction, which again is a subclassification of a double displacement reaction. Any questions on any of that there? Okay. All right, so let's talk a little bit about acid and bases. So as I mentioned before, what we've been talking about sort of up until this point is sort of the big classification of double displacement reactions, which as we just saw there in a lot of those examples, a more specific classification is a precipitation reaction. And now another specific sort of classification that falls under double displacement is an acid and base reaction. And again, as we've been talking about, the precipitation reaction accounts for the solid being formed. And acid-base reactions typically is the formation of water is really sort of what's happening here. And that is really the reason the reaction is taking place. So when we look at acid and bases, an acid is anything that will have the ability to produce hydrogen ions in solution. When we talk about acids, the hydrogen ion is used. Also, a polyatomic ion, the hydronium ion, H3O plus, is used. They are essentially used interchangeably in acid-base chemistry. So you'll sometimes see people use H3O plus. You'll sometimes see people use just H plus. They really mean the same thing when you're talking about acids and bases, which you'll learn a little bit more about when you get into 200B. But they represent really the acidic part of the solution. So they are sort of used interchangeably. In addition, H plus is sometimes, again, also referred to as a proton when you're talking about acid and bases. And that is because hydrogen has 1 proton, 1 electron, and no neutrons, which means in order for it to become +1, it has to lose its electron, which leaves it just a proton. So proton, hydrogen ion, and the hydronium ion all refer to pretty much the same thing in acid-base chemistry. They all refer to basically the acid, and that's what the ability is. And when we talk about that, is the ability of something for when it goes for a swim in water to have the ability to produce free H plus floating around. That's why something like we saw earlier, like hydrochloric acid, is a strong electrolyte. When hydrochloric acid goes for a swim, it will 100% break apart into H plus and Cl minus ions. And because it's able to produce a lot of H plus really quickly, it is considered a strong acid because of its ability to do that. Now, bases, on the other hand, typically will have the ability to produce hydroxide ions, OH minus in solution. So bases pretty much will produce OH minus in solution. And it's really the same sort of thing. It is the ability to produce sort of in water, if you will, free OH minus ions floating around. And as you'll learn when you go to 200B, the ratio of how much H plus to OH minus are in the solution will determine whether or not the solution is acidic or basic. So if you have more H plus floating around the solution, it's going to be more acidic, like your litmus paper will turn red. And if you have a lot more OH minus in that solution, your litmus paper will turn blue and it'll be more basic in that particular case. So when we take an acid and a base, and specifically really a lot of times a strong acid and a strong base, we really will produce two things. We will produce salt and water. So when we take an acid, like say HCl, and we react it with a base like sodium hydroxide, this is an acid-base reaction, but if you look at it, it is also a double displacement reaction. That's a positive-negative guy. That's a positive-negative guy. And we're going to get the same thing that's going to happen. Our H and our OH will come together, and our sodium and our chloride will come together. They're going to switch partners. So we will get basically the two units, H plus and Cl minus, Na plus and OH minus, and these two guys will come together. When those two guys come together, that is how we form water, H2O basically, right? Two hydrogens, one oxygen. When H plus and OH comes together, that is how we form water. And the other two guys will come together, our sodium and our chloride, and that will make NaCl. And that is what is referred to as a salt and water. A salt is a fancy word. I'm not really sure how fancy it is, but it's a fancy word for basically an ionic compound. So basically it's an ionic compound, it's a salt. In most cases, when you have an acid and a base coming together, the salt is frankly like the spectator ions. They're just the guys kind of floating around in the solution basically as ions in most cases. Although it is possible to have a salt that's insoluble, but probably 9 times out of 10, the salt part, or even more than that, will be soluble and just kind of floating around as ions in the particular solution. So always when you take definitely a strong acid and strong base, always in that case, it is the H from the acid and the OH from the base that will always make pretty much the water part of it. And then you basically just put the other two guys together. So as you can see here, this is a double displacement reaction. It is more specifically classified as an acid-base reaction, or sometimes referred to as a acid-base neutralization reaction. The reason why this reaction is taking place is right there. It is the formation of water. So unlike in a precipitation reaction where you could see the solid, a lot of times you can't really see water being made, but it is being made, and that is really the reason behind that reaction taking place. Any questions on that there? There are some strong acids and strong bases, which are pretty much good things to know, because if you sort of know the strong acids and strong bases by the process of elimination, you pretty much can determine that something else is probably going to be a weak acid or a weak base just by the process of elimination. So some strong acids and strong bases, I would say these are your big strong acids, which are really good to know for our class. And as you move on into 200B, that's your hydrochloric acid, that's your nitric acid, that's your sulfuric acid, that is your perchloric acid, that is your hydrobromic acid, and your hydriodic acid. So these are kind of the 6 strong acids. As you can see here on that list, that should probably take you pretty much through most of those. So hydrochloric acid, hydrobromic acid, hydriodic acid, perchloric acid, and sulfuric acid, and nitric acid, those are 6 strong acids. Pretty much, I would say, if it is not one of those acids, you could probably assume it's going to be a weak acid. So that's a good way to sort of just quickly figure it out. Later on, if you take 200B, you'll figure out some other ways to figure it out, but that's really a best way to kind of do it. So these are really strong acids, which means all of these guys will 100% when they're in solution fall apart into ions. They will break apart into ions. And you'll have a lot of H plus being formed really quickly, which is why they're considered strong acids, because when they go for a swim, they produce a lot of H plus really, really fast. And that's basically your definition of an acid, is the ability to produce an H plus. So because they're able to just completely break apart, you're basically flooding the solution with a lot of H plus and making it more and more acidic in that case. Now, in terms of strong bases, I will say most strong bases will actually have hydroxide in the formula. So some strong bases, potassium hydroxide, sodium hydroxide, little lithium hydroxide, If you kind of go to the periodic table and you look at group 1 and group 2, which are your alkali and alkaline earth metals, the word alkaline means basic. So a lot of our strong bases come from group 1 and group 2 on the periodic table. Frankly, if you go down from lithium to potassium and hang a right at potassium to calcium, strontium, barium, all those guys with hydroxide are going to be probably strong bases. So if you look on group 1 and kind of come down over to like where calcium is and down, any of those guys with hydroxide will probably be strong bases, you know, like calcium hydroxide, strontium hydroxide, etc. So that's really where you can find most of those guys. They definitely usually will always have hydroxide in it. Now, not all bases actually will have hydroxide in the actual formula. A lot of weak bases will actually not have hydroxide in their actual formula. But what happens with a weak base, like, for example, ammonia, which is probably the most common weak base that you'll come across, NH3, which is ammonia. What happens with that is, although it does not have hydroxide in its formula, when ammonia is in solution with water, what will happen is it will actually grab an H plus off of the water and it will produce NH4 plus, and it will then make water into hydroxide. So it has the ability to produce hydroxide by removing an H plus from water, and that is why it's considered a base. It's considered a weak base because it's got to go do that. It's got to go do a little reaction to produce the hydroxide. Something like sodium hydroxide, which is a strong base, does not need to do that. It simply just needs to go for a swim, and it's just going to break apart and produce hydroxide right away. And that's why it's a much stronger base than, say, ammonia, because it doesn't really need to do anything but just go into the solution and it will dissociate apart. So again, kind of group 1, group 2, kind of coming down to potassium, hang a right, and then down. Any of those guys with hydroxide pretty much going to be a strong base. Again, those 6 acids are going to be your strong acids. And again, by more so for our purposes here, process of elimination, it's not one of those, so it's probably going to be weak. Is a good way to know it. I would say you probably should remember ammonia as a weak base because that really does pop up a lot in all chemistry classes. So that is definitely a weak base. As you can see as well, we have our arrows heading in both directions like we talked about earlier with our weak electrolyte. It is a reversible sort of reaction that's going to happen. So when you take an acid and base, as we talked about, you do get this acid-base reaction. It will produce a salt and water. You could also write your total ionic equation. And if I do that, because hydrochloric acid is a strong acid, it will break apart into H plus and Cl minus. Sodium hydroxide, which is a strong base, will break apart into sodium ion and hydroxide ion. Our sodium chloride, which is our salt, will also break apart into a sodium ion and a chloride ion. And here, water, which is a liquid, much like our solid, will stay together and it will not break apart. And if we look in this case for our spectator ions, it is the chloride and it is the sodium, which if we cancel out, will give us the net ionic equation, which is basically the H plus from the acid. We'll go find the hydroxide from the base. H plus and OH minus has an extremely strong attraction force to each other. If they're near each other, they're going to probably want to come together in most cases. And that is going to form our water here. And by the way, that is pretty much your net ionic equation for every single combination of a strong acid and strong base. So if you get down to the net ionic equation for a strong acid, strong base, it is always the formation of water, which is again why this is referred to as a neutralization reaction, because basically water is ultimately what is being formed. And that again is one of the 3 reasons why a reaction takes place, is the formation here of water. Any questions on that there? Now, what happens though if we did put together, for example, a weak acid, right? And we talked about a couple of weak acids, for example, like hydrofluoric acid is a weak acid. We also talked about acetic acid there we saw earlier as well. These are all weak acids. So what happens if I did put together, for example, a weak acid with a strong base? What would actually sort of happen? So let's take a look at what will happen in that case, in case you come across it. So let's say we put together hydrofluoric acid and sodium hydroxide. So we're going to put together hydrofluoric acid, which is a weak acid, with sodium hydroxide, which is a strong base. Once again, this is still going to be a double displacement reaction, positive, negative, positive, negative. So we're going to switch partners. And just like we saw previously, it is going to be the H and the OH is going to come together to make water. And it's going to be our sodium and our fluoride in this case that's going to come together, Na plus and F minus, to make sodium fluoride. We know that's going to be aqueous because it's sodium involved. So this makes our water and our salt in this case. Yeah. And again, just swapping partners there, basically. Any questions on that there? So this would be our balanced molecular equation. We got our states. If we went to our total ionic equation in this case, because this is a weak electrolyte, as we talked about, right? It's a weak acid, which makes it a weak electrolyte. Will it break apart or mainly stay together? It will mainly stay together, which means when we get to our total ionic equation here, we're actually not going to break it apart. We're going to keep it together because it's a weak acid and a weak electrolyte. We will break apart our sodium hydroxide because that's a strong acid, which makes it a strong electrolyte. We will not break apart the water because it's still a liquid. And our sodium fluoride is an ionic compound and a salt, which will break apart into sodium and our fluoride. So our total ionic equation will look a little different because we're not going to break apart the weak electrolyte, which is our weak acid, or even if you had a weak base, same idea here. Also, what's going to be different is how many spectator ions do I have in this case? I have just one, which would be the sodium, is the only spectator ion that is present. It is the only one that is the same on both sides. So this would be actually our only spectator ion, which we would also cross out. And our net ionic equation will also look a little different. We will still have the HF together, and the hydroxide will make our water, and we will have this F minus still hanging out in that solution. So when we look at like the beaker in this case, we basically have the HF, we have the OH minus and the sodium flowing around. And again, we do have a little bit of H plus that will break apart. So that's where the water will come from. But we will have just really that sodium ion as sort of our spectator ion that's floating around in this particular solution. So if you come across something that's a weak electrolyte, which will be a weak acid or weak base in most cases, again, you want to keep that together, just like we talked about anything that's a solid, liquid, or in most cases a gas. You would want to keep it together in that total ionic equation, which obviously means it does follow through to your net ionic equation as still staying together. Any questions on that there? Yeah. Still, ultimately here, the formation of water is what's happening, which is why this reaction is taking place. All right. Now, in addition to sort of the formation of water or the formation of a solid like a precipitate, we can have double displacement reactions that will actually end up with the formation of a gas. So sometimes a double displacement reaction will actually lead to gas being formed. And there's actually sort of two ways that a gas can be formed in these type of reactions. One way is directly. So for example, here, if we look at potassium sulfide and some sulfuric acid, again, double displacement reaction going to happen. Potassium and sulfate will come together to make potassium sulfate. Our hydrogen and our sulfide will come together to make hydrogen sulfide gas. That is hydrogen sulfide gas because the symbol there is G. That is not an acid like hydrosulfuric acid because it's not aqueous. So this is a gas being formed. This is what is sometimes referred to as a direct gas formation as a result of just the two ions switching places. More commonly, probably, is the formation of a gas as a result of something going through a decomposition reaction or breaking apart. And that's what we see here. In this case, we have a positive, negative, positive and negative. Our potassium and sulfate is going to come together to make our potassium sulfate. But when my hydrogen and sulfite come together, we actually make sulfurous acid, right? H2SO3 is sulfurous acid. Sulfurous acid will not hang around a very long time. It will kind of immediately go through a different type of reaction, which is known as a decomposition reaction, which basically means it will break apart. And it will break apart, in this case, into water and SO2 gas. So this is sort of a double displacement reaction followed by one of the products going through a decomposition reaction, basically breaking apart and forming a gas. This also happens a lot of times when you look at something like Alka-Seltzer, things like that. Plop, plop, fizz, fizz. If you take a little hydrochloric acid, a little, say, sodium carbonate, it will do a double displacement reaction, positive, negative, positive, negative. H will come over here, sodium will come over here, and we will get a little sodium chloride plus a little H2CO3, which is carbonic acid. In this particular case, we'll do a little 2 there and a 2 there to balance it. But it's actually this acid here, which is also another weak acid. This is carbonic acid. Carbonic acid will almost immediately break apart into water and CO2 gas. So that was like that plop, plop, fizz, fizz. You ever see like an Alka-Seltzer commercial, pop the little Alka-Seltzer, starts bubbling and all that kind of stuff? That's basically what's happening. It's producing CO2 really quickly, and those are all the kind of the bubbles and stuff that you see. So these are what I refer to as sort of indirect gas formations, but they happen as really a result of one of the products going through a decomposition reaction, which is essentially breaking it apart. Any questions on those? Here's a little table that kind of shows the different sort of scenarios. If you take a metal and it has sulfur in it and you react it with an acid, you'll get directly hydrogen sulfide gas as a direct gas being formed. If you have a metal that has carbonate in it and react it with an acid, you'll get carbonic acid, which will go through a decomposition reaction and make that CO2 like we just saw. If you have a metal that has sulfites or a metal with hydrogen sulfide and react it with an acid, you're going to make that sulfurous acid, which will produce that SO2 gas. And actually, if you have ammonium and you react it with a base, you're going to get ammonium hydroxide, and you will produce ammonia, which is a gas. And that's a very common thing. So you take a little sodium hydroxide, for example, and ammonium chloride or something like that, and it will generate basically NH3 gas as a result of that. You actually do that in 200B in an experiment. Any questions on that there? One last thing here to talk about these type of reactions, which is we've gone through, our molecular equations, which is we just write everything like normal with the proper formulas. Again, our total ionic equations, which is where we break apart anything that's a strong electrode into the ions. We find our spectator ions, leads us to a net ionic equation, which is basically the reaction that describes exactly what's happening in this type of reaction is taking place. Just so we're all clear, what we've been talking about pretty much today in terms of types of reactions are double displacement reactions. And all double displacement reactions usually results from the combination of two ionic compounds always. And as we've done in a number of these examples, everybody's just going to switch partners and will form two new ionic compounds on the product side. And as we saw in certain cases, a subcategory of this is a precipitation reaction, where one of these guys make a solid. Another subcategory of this is an acid-base reaction where one of these guys make water. So, and these guys make water. So if we looked at this reaction that we saw a couple of times today, a little NaNO3. No, let's see this backwards here. Shoal. We look at NaCl plus some silver nitrate, making our silver chloride and our sodium nitrate. This reaction is classified, can be classified as a double displacement reaction. This reaction could also be classified as a precipitation reaction. It would not be classified as an acid-base reaction because there's no water being formed in this case. So this is one of those two classifications. And if we look at one like we just looked at there, little HCl, put some sodium hydroxide, make some water and sodium chloride. This reaction could also be classified as a double displacement reaction, but also could be classified more specifically as an acid-base reaction. So as we see here, and as we'll continue to see when we talk about the rest of this next time, you could classify the same reaction multiple ways, but all reaction classifications pretty much fall under those two big umbrellas of double displacement reaction, which is essentially what we focused in on today. And next time we'll talk about redox reactions. And both of those big classifications really account for three reasons why a reaction takes place: formation of a solid, formation of water, or the transfer of electrons. Any questions on any of that there? All right, we will lay up the torture.